And when it comes to competition, we have like 25% so we have like large attack on Polkadot network, you can expect 4 times higher block speed. But blockchain is slower, so the attackers are not getting that much competition. And it's costly.
If I run the computer, say, was, isn't that like give me some kind of burning up by the ones that just
No, because the section the biggest thing validate, but the only one can do is have to know the file. And then the out that get generated so it can also happen that a single validating issue across the road is like you can make any sort of publication. Say, okay, this guy has an issue with a block this much time. No, it's better. They're not great. Okay, and finally, we can take a look at the newest iteration of the block offering mechanism, and it's called Safrol, or previously was called Sassafras. They're essentially 2 names for the same thing. There were just some simplifications in the implementation and the design, and they renamed it slightly. And Safrol is not something that is being used in Polkadot right now, and it's probably not going to be used in the Polkadot 2.0 we have today. It is intended to be used when Jam launches. And actually, I have a disclaimer about Jam on the previous lecture, which we missed because launch caught us off guard. So who here has heard about Jam, excluding my lecture mentioning the Jam name? Okay. So Jam is the next iteration of the protocol. And I hear a lot of misconception about what it is and what it isn't. In general, everything that is currently possible to be done in Polkadot 2.0 will be possible to do in Jam. Parachains, just like they exist today, will continue to exist in Jam. It's an abstraction of the current way the protocol operates, written from scratch in different languages to have better diversification of clients, to prevent potential bugs and make the whole system more resistant. It's also enabling some new stuff. I will not be getting super deep into it now, because at the end of the whole PBA, there will be a short Jam module where we'll cover that in more detail. I'll also be doing some demos there, and then we can have more of a conversation about that. But all you need to know is what you're learning here is not getting outdated. Substrate can and will still be used to build parachains. All the staking stuff I mentioned is probably still in Jam, and all the different sharding mechanisms I will be explaining in the future lectures are still core in Jam. Okay, so Safrol has 2 main things. It really focuses on eliminating forks. So Babe has this big downside that sometimes multiple people have won the lottery. And it tries to reduce the reliance on Aura as a backup to have even better security and even better liveness under consistent DOS attacks on the network. But still tries to maintain privacy for the block authors for as long as it can. So imagine a situation where instead of having a threshold, in this case, we do have a single winning guy, but a different way of establishing who is the author would be to, instead of having a threshold, just try and look for the lowest winner. To do that, as I mentioned, we would actually have to sort all the tickets, have to sort all the lottery tickets, which are secret. So that is a bit of a problem. So the two main difficulties here is to know the lowest one, we have to actually order them, but they need to be anonymous. But they also need to be validated so that we know that the tickets are provided by, actual potential validators. So wait, anonymous but validated, how do we reconcile all those things? How can they both be validated and anonymous? So one way of doing that is we can use mixnets to obfuscate the origin of a ticket. A validator randomizes the ticket, and then instead of sending it to someone else immediately to the destination, he sends it through a list of relayers, essentially like a Tor network, an onion network. So it obfuscates where it comes from. Then you don't know if the previous hop is the originator of the message or just a relayer, one of the validators. And then instead of using standard VRFs, we are using ring VRFs, which are essentially expanding the scheme to, instead of proving I am the one that randomized this number, they're proving I am one of the validators that randomized this number. So it says that this number was randomized by a validator, but it doesn't tell you which one. And then later on, an actual specific validator can say, okay, this ticket that won was mine, and there's a way for him to prove that this ticket was actually his, so we can claim his slot. Does that make sense? Any questions so far?
Just like a question, like, is it the blind ring VRF? I believe this is the name, where it's kind of mixed with ZK, where I don't know who, but I can verify that this validator is part of this set of validators. Is it correct?
Yeah, it is using essentially a ZK to provide an anonymity set between all the validators. So you can initially prove that it is it's a unique ticket from. It's a ticket from a unique validator within this anonymity set. And later on, through another proof, you can make like an owner proof that we know that it's a validator, but we can also prove it's specifically this validator when you want to announce it. So there are like two levels of proofs. First one, the generic validator proof, the uniqueness proof, and then I am the owner proof. Question?
So you mentioned the relayers, like the message hops through different bunch of relayers. Can you explain what is a relayer?
So a relayer is essentially, explaining onion. So the problem is if eventually the tickets need to get to other validators and all the tickets need to be known by all validators. We could just, have your own tickets and gossip it to other people. The problem is they can essentially monitor the network and see where the ticket originates from. So we need to have some proxies. Instead of just giving the ticket to the destination, you first give it to some intermediary, and this intermediary on your behalf passes the ticket over. And then whoever receives the ticket knows that they got it from the intermediary, but they don't necessarily know who was, the hop before that, your actual you that sent the ticket over. So if you add multiple hops along the way, it's much, much easier to obfuscate where the ticket actually comes from, because it goes through multiple hops of like randomly generated nodes in a mixed net, and gets mixed up in this net before it ends up in this destination. So for someone to figure it out, they would have to track it on a very large scale and figure out all the previous hops. And on every single hop, the message is encrypted. So you pretty much only know the next destination of the message without knowing what the message actually is. And it gets slowly peeled away. Every encryption level gets slowly peeled away as you transfer it over to the final destination. If you want to learn more about it, read about onion routing or the Tor network. This is a pretty well-established, or mixnets, a well-established protocol for hiding and obfuscating the original origin of the message. Question?
It might be a naive question, but I'm kind of concerned about how fast is that compared to Babe?
How fast it is compared
Yeah,
to that?
because it should be like the next block, correct?
Mhm.
So like the 3 steps, including like generating the proof for each process, for each step, does it require like much processing and much time in?
It definitely takes more work to do it. The ring VRFs are heavier to compute.
Yeah.
The signatures are heavy to compute. But as far as I know, it's not meaningfully slower here. There is not that many signatures that need to be done. I don't know the exact timings of how much slower it is, but for sure slower, not enough to not justify it.
Great, thank you.
Any other questions? Cool. So, equivocations. I already kind of explained what an equivocation is. Generally, ambiguous or conflicting statements. An example, another one. So imagine you have a single phone number. You met Alice and Bob, and you have given them your actual phone numbers, but you give them 2 different phone numbers. At this point, we don't even need to check the exact numbers you've given them. But if Alice and Bob meet up and they share your number and they see that they are conflicting, they're different, they immediately know you lied to one of them. It doesn't matter which one is correct or incorrect. They know you gave them conflicting statements. You equivocated. And this concept is very commonly used in blockchains as an example of a malicious behavior that has to be punished. On many different levels of the protocol, we are expecting a single action to be taken, a single statement to be published. And if someone equivocates, and if that is detected, it has to be reported, provided with a proof, and someone will be slashed for it. An example of an equivocation is the block offering. Maybe you issue 2 blocks. In Grandpa, there is a lot of voting we have to do. We have to vote what I believe is the best chain. And if you vote on 2 different conflicting chains, you give conflicting statements, you will also be punished for it. And the proofs, in this case, it's pretty nice because the proofs are so obvious. You have 2 conflicting statements signed by a single person. It's very easily verifiable that this is incorrect, that this is a proof of someone performing fraud, equivocation. So it can be permissionlessly provided by anyone, not just a validator. There's a small fee, you have to pay for it, but if your proof is actually correct, the fee will be returned, and you're doing justice, you're helping the protocol. So that's why we don't have to collect a fee for it. Okay, any extra questions about block offering? Because it's a pretty short lecture, and we are done with it, and can proceed to the next one. Questions?
So just to clarify in my head, is Safrol does it replace Babe, or is it still the backup after Babe? So in other words, just replace Aura.
It completely replaces Babe.
Okay, so
because then there is no longer a reason to have the fallback like. So Babe had a fallback to Aura, and Safrol doesn't need to have the fallback to Aura because there's always a ticket with the lowest value.
Other than the answer to the question here, that it's potentially a bit slower. That's why I was thinking perhaps Babe is still kept as option 1.
I mean, right now we don't have Safrol in the actual network, but I don't think this is the intent to have the backup like that.
So in your slides, there was, or maybe not your slides, but in the slides, there was said in Safrol that it minimized the aura, but it actually negates it. Does it need the aura?
True.
So maybe there is a mistake. Just saying.
It never has to depend on it. Because the nice thing with not having this arbitrary threshold, there is always the lowest ticket.
Kyle here. Just wanted to ask, how many hops in the mixnet, or is it determined by the VRF?
How many what?
Hops in the mixnet.
Good question. I think it's unclear because it's being worked on for Jam. I don't remember if the Jam paper specifically says how many hops are needed. I think it's a hard-coded value. But I don't know the I think it's probably like 3 or 4 hops, not more than that. And it's already giving you enough security. But it's just a specified set value. It doesn't have to be super dynamic. Any other questions?
Who are the participants of the mixnet? The servers that themselves, the validators, the users?
I think the idea was to have the mixnet not be comprised of validators, have an external incentivized scheme. But I don't know what they settled on in the end. Like, it's still something that's being worked on and developed. We don't have a fully fleshed out, done in production implementation. So I think they're still exploring both options.
Okay, and just another clarification. So it's not ZK based, it's like Tor-like. So you just mix a few hop in nets, and it's not like Tornado cache that mixes the.
I mean, Ring VRFs and ZK are not that far apart. There are some similarities between the two, and they provide similar cryptographic primitives.
Okay, thanks.
Because you essentially are doing a zero-knowledge proof of, we know that a validator signed it, but you're not leaking all the information. It's like a limited knowledge proof. It's very, very similar mathematical and cryptographic mechanisms are being used here.
I see. Thanks.
Are the hops in the gray paper, or they will be in the gray paper? Because I don't remember reading about them.
They should be. I think they omitted them for some time, but the plan is to add them, and it's like, there should be hops. And
But I don't think there is anything written about them yet.
I am aware.
Okay.
They should be there. I think they have been omitted so far because most people are not worried about Safrol yet. And there are many sections in the gray paper that will be expanded because they are not exploring things in depth enough. And the hops are needed there. Otherwise, it doesn't fully keep all its promises. And just so everyone is aware, gray paper is the formal specification and documentation for implementing the Jam. So the next iteration of Polkadot. Any other questions before we proceed? Good. Okay, then. Now we are going into the data availability lecture. So this is the first part of a 3-segment lecture about the ELVS protocol. We're slowly discussing the sharding aspects now. Okay, so the main actors we'll be actually discussing here is the collators and validators. Primarily, it will be very heavy on the collator side. Specifically, we'll be looking into a process I call the assignment, and then a pretty well-established process called bucking, which is essentially validators putting some stake to ensure the correctness of a parachain block. Then we have the availability, which is making sure that any data necessary to verify a specific parachain block is made available for some time. And then how we exactly achieve this availability through erasure coding. So the last time we looked into collators. And we mentioned that collators are the ones collating transactions and building parachain blocks. We have a lot of similar names for same stuff. So parachain block, we also call a collation. A collator produces a collation. This is a parachain block. And the main purpose of a collation is to collect transactions, bundle them up. Then we go into the backing stage where we try and assign responsibility. We try to have a specific validator on the hook for that collation. Then we go through the availability phase. This is ensure that if something goes wrong, we have all the items necessary to find who is actually guilty. We have all the data to verify it again. And then we'll be going to the actual checking of the data with the approval checking mechanism. Backing is not about checking correctness. It's about assigning responsibility. Approval checking, which will be discussed 2 lectures from now, which is where we will be actually verifying correctness and potentially slashing people. And disputes is where the slashing will probably occur. This is where validators disagree on the correctness of a state transition. Okay, so let's look into the assignment. So assignment is a process that is operating only on the active validators. We had our active validators given to us as a result of the staking mechanism. Let's assume we have 1,000 validators in the active set. And we are getting those every 24 hours. They might be a different active set. And they are the core players in our Polkadot protocol game for those 24 hours. And every session, which is 4 hours in Polkadot, the parachain consensus, which is all this ELV's logic, is taking those 1,000 validators and further partitioning them into smaller groups. In Polkadot, those groups are right now of size 5. So we are taking the 1,000 validators and splitting them into groups of 5. And each individual group is called a backing group. So we're splitting them into smaller groups called backing groups. And this is only a slight teaser, but every single backing group is essentially mapping one-to-one to a Polkadot execution core. That's why I mentioned how many execution cores we can have, number of validators divided by 5. Like, this is where this is actually coming from. And these assignments, each backing group is essentially assigned to an execution core. They're mapping one-to-one, but the assignments will rotate over time. So imagine you and your 4 validator buddies are assigned to a specific execution core, let's say number 1. And this execution core is connected to a specific parachain, let's say something like Akala. You are validating, you are in a backing group for the parachain for only a set amount of time before you rotate to a different execution core, potentially serving a different parachain. This rotation happens every 10 time slots. So every 10 time slots, you and your buddies in your backing group are getting switched to a different execution core. And a single execution core connected to a single parachain essentially can handle a single parachain block every 6 seconds. This is what an execution core gives you. It audits, it validates a single parachain block every 6 seconds. And then, after 10 blocks, our groups are rotating around between the execution cores. So this makes it so even if a specific backing group is malicious, or maybe they just go down, they are having some issues, we're essentially rotating them around, so not a single parachain will be affected by them for too long. Sure, they will have a tiny bit of downtime, but then we spread around the risk and the responsibility around different execution cores. Or alternatively, if this group is actually malicious and they're trying to actively DOS a specific parachain, well, they can only DOS them for a very short period of time before being assigned to a different execution core and potentially a different parachain, which they are not interested in actually DOSing. And we'll be further exploring this whole execution core perspective, how work is being assigned to them in the Agile Core Time lecture we'll be having, I think, tomorrow. So collators, as I mentioned, they collect all the transactions from that specific parachain. They have a transaction pool from which they select them. And they create a collation. And they need to check, send a message to the relay chain to figure out who are the current validators assigned to the backing group responsible for their parachain. Once they get this information and they have the para block, they essentially can send it over to their designated validators in the corresponding backing group. So now we can finally arrive at the backing stage. We just send some collations to the validators in our backing group. What happens next? So validators in the backing group are often called backers for those para blocks that are coming over. They're essentially backing them. They're putting their stake, they're putting their weight behind them, trying to vouch for their correctness. So in this specific image, what we're actually trying to show here is that all those little pink squares here are individual parachain blocks. And we have some backers, those white pills, are representing some relay chain validators assigned to a specific group. So in this case, we are having some collators sending over a parachain block to essentially the group of bouncers. They're guarding the access to the relay chain. They're receiving the parachain block from the external world, connecting to the collators and receiving the data from them. And we can zoom in even more and actually see that. So that's slowly explaining this big diagram we've seen in the first lecture. And they're kind of like the bouncers of the protocol. They're the main way the relay chain is exposing anything to the outside world. They have to be pretty selective who they allow to connect. They need to verify the collators. They're keeping pretty strong tabs on the reputation of tracking collators. If the collators are providing collations that are not sufficient, that are not good, that are incomplete or corrupt, they're decreasing the reputation and potentially closing down the channels to prevent any sort of DOS attempts. But I mentioned that the backers, they need to actually back the collation. They need to vouch for them. They need to put their stake behind it. But for them to be sure that they can put their stake, they actually need to verify the correctness, at least from their own little perspective of this specific parachain block. They cannot simply blindly trust this random data coming from the external collator. And to perform those checks, from their perspective, to know that this is correct, they need to be utilizing something we call a PVF. This is a parachain validation function. So a PVF is essentially, imagine you have the previous state of a parachain, and imagine you have all the transactions. This is essentially what is stored in a parachain block, a bunch of transactions. And assuming you have the state transition function, aka the runtime of a parachain, you can compute the new state. You just apply the transaction based on how the cookbook tells you to, and you mutated the state from previous to next one, a state transition. And a PVF It's an encapsulation of that process. It's essentially a function to which, given some inputs and giving some state, is the resulting state the one that was promised to me? So whenever a parachain, whenever a collator sends over a parachain package, it has to be re-verified, re-executed by some validator to know if it's correct. So just to make sure everyone is aware, if we have some transactions and a POV, this is a proof of validity, this is the previous state, this is the smallest minimum amount of state needed to verify this transaction, this block of transactions, and then we have our cookbook, our runtime, we can arrive at the new state root that was promised to us. And if we actually arrived at the one that they've given to us, we know that this execution is correct. Any questions so far?
Hi, Satish here. Couple of questions. One is the core definition. You mentioned that 5 validators is what we define a core as. Any particular reason it is 5, or why can't it be 3? Because previously, if you run the standalone chains, the 3 validators can actually finalize a chain. So why is it 5 on a relay chain?
Can you repeat the question, but slower?
Okay. So in a standalone, in a solo chain,
Yes,
you
the
can
solo chain.
finalize the chain by running 3 validators.
So first of all, there are no solo chains here. There are
No,
parachains
Correct.
submitting some packages to be verified by the relay chain.
Correct. Now, my question is, why is the core defined as it need to have 5 validators? Why not 3?
Why is the backing group 5 validators?
Yes.
So it is simply to spread the load evenly between the validators. If we made it so you can submit your parachain block to any validator, this will result to some validators being potentially overloaded, others being underloaded. This will potentially result in you sending the packages only to your preferred validators.
Mhm.
And we want to have a pretty even spread of responsibilities and load within the system.
Okay, so it's to manage the workload and the failure conditions?
To do what?
To manage the workloads and the failure conditions? Okay, I'll drop it. So the second one is, we talked about the backers moving from one parachain to another.
Mhm.
When the movement happened, does a group also have a different mix of backers getting in, or the group stays as it is?
So the groups rotate around every 10 blocks and they get reshuffled every
Okay.
4 hours. So you're staying with your 4 buddies for 4 hours and then everyone is getting reshuffled.
Got it. Thanks.
And then every 24 hours, everyone in the active set can be reshuffled because there is a new election coming over.
Maybe one thing about the 5 validators. I mean, it's for security reason, you can actually have 3 validators. And there have been like people at the research team suggesting we can actually do this. The whole point is that you want to be the system as scalable as possible, right? You have these 3, 5 guys that they are basically the entry point, and at the entry point, at the core, and they check everything, right? And then you assume that this most of the time everything is correct, so it's kind of optimistic, right? But after this, you have actually the secondary checkers and de-escalation effect. Probably see later about disputes and everything. That if something bad happens, then this escalation effect brings more validators to check, right? It's actually a very scalable system, but very secure because everything gets checked all the time. And this is very different from optimistic rollup, right? Yeah.
Hey, Marcin here. So the collators are always producing block for the same parachain, or they shuffle. They're producing for the same parachain, collators.
Correct.
Yeah. And the validators are validating blocks for different parachain because they are shuffled.
Correct.
Okay, that was just for clarification.
Yeah. So for 10 blocks, a group of 5 validators essentially handles a single parachain, and then they go to a different one. Collators stay constant for a specific parachain.
Another question related to validation as well, the validator as well. You said like the current active validator assign the next set of validator for the next iteration. Let's say this. When exactly they are assigning? Is it like when they start or by the end? Like it's 24 hours, so they are doing it from the first hour or by the end of the last hour?
So you're asking when is the next active
The
set
assignment
node?
of the next set of validators.
It's a good question. I don't exactly know when is it known. I think it's not that long before the set change actually happens. Probably within the last hour is when the results are computed and made available. But I'm not 100% sure timing-wise when it
I'm
happens.
just like, it might be crazy idea, but what came to my mind is what if, as a parachain, I know the validator new set was assigned 2 seconds or 3 seconds because each slot is 1 second, and then I need to like do this kind of math thing just to know who is the backer. What if I have kind of latency in the network, stuff like this? So this is what came to my mind. So I might be crazy, but yeah, that's why I'm asking this question. Thank you.
So computing from a collator perspective, computing who is your validator is not that complicated because the rotations are easily predictable. Like the groups are rotating, they're not getting shuffled every 10 blocks. So if you know the arrangement of groups for that specific session, aka 4 hours, predicting who will be your group is quite
Whatever. And yeah, this is my point, the gap. Because if I have a latency and the new assignment was like the last second in the last iteration, I might have a gap as a parachain.
Why would you have a gap?
Because of maybe there is like I didn't like it's seconds. I'm just like I might be because of the day lunch. I'm not focusing well, but as a parachain, maybe there's a latency in the network. I was disconnected, whatever. So I don't know the backers. So the assignment as a collateral, I will not know who is my backer.
This gap could maybe potentially occur on session changes. This is where the validators are getting reshuffled into the backing groups. And I think I don't remember if it's still happening, but we definitely had cases where there was like a single time slot being missed on session changes. So every 4 hours, parachains were missing like a single block. This is fixable by some like optimistic computation of what is the next session arrangement, yada, yada, yada. I don't remember if it's still happening today, but every 4 hours missing a single time slot is not a particularly big deal, and it definitely can be fixed.
Is it clear which validators are assigned to what parachain? Like, are other people aware of that?
Yes, this is completely public information.
So when the validators are selected to, I guess, create the proof, is it like through a VRF that they're selected to create a proof, or is it just, yeah, I guess, is there like some randomization?
So it is public information. There is no need to keep it secret. We are using essentially the randomness coming from the previous session to generate the new arrangement, the new distribution of validators into the groups. So you can at most predict the next session arrangement and not more into the future.
Got it.
So just to confirm, like a single parachain has multiple collators, right?
Correct.
So what is the mechanism behind, so do these multiple collators send unexecuted transactions to the validators, or it's just like one collator that is like sending transactions after picking it up from like a transaction pool to the validators?
Mhm. So ideally, a parachain can have a single collator. This could perfectly work. You're very susceptible to denial of service attacks, but other than that, perfectly functional. If you're having multiple collators, then you need to have some authorship throttling, like we discussed in the previous lecture. You can use something simple like Aura to make it so for every single time slot, only a single collator is actually allowed to produce a block. And then this Aura mechanism, a single collator being allowed, is baked into the runtime of this parachain block. So the author is actually verified in the state transition. And if a different person, if a different collator issued this block, which wasn't allowed to, this would essentially result an error when the state transition is reevaluated on the relay chain. If a parachain is not using a throttling mechanism, they're just allowing anyone to nilly-willy produce a parachain block, which is something they can do. This can create a situation where for a single time slot, we can have multiple competing parachain blocks. Essentially, the parachain is forking. And then it is up to the backing group validators to choose between those available parachain forks. They, and I will be getting into that in a second, they can bug them after they do some checks. And at this stage, it is still possible to have multiple backed parachain blocks. Okay, we say multiple backable parachain blocks. But then the next relay chain block author selects which of the backable parachain blocks actually makes it into a relay chain block. So he has to kind of choose which fork is the canonical for now. And this can get even more complicated. Is at this point, suddenly Babe also forks. Then maybe you have two relay chain blocks, which can choose different forks of the parachain. So the whole forking can get pretty messy here. This is why we don't like Babe forking, and Safro will hopefully fix that.
So you mentioned more than one block being given from the parachain. So is that the scenario when more than one cores are assigned to the same parachain? Like, is there as such thing as like assigning more than one core to a single parachain, or is it like always 1:1?
So there are two different options here. If they are not using something like Aura, it is possible for, you mentioned the word blob, they're providing two collations, like essentially the parachain forked. But eventually one will have to be chosen. There are other ways though. This will be explored in much more detail in the Agile Core Time lecture, but there are ways for a single parachain to occupy multiple execution cores. And then what can happen is in a single relay chain time slot, a parachain will produce multiple sequential parachain blocks. And both of them will, it's not a fork, they're sequential. And both of them will be computed, executed, and backed in different execution cores. And both of them will be asynchronously in this case, re-executed and revalidated by the validators. So that effectively increases the throughput of a parachain while still being synchronous.
And that's possible even now with Polkadot?
It is possible right now, yes.
Okay.
It's called, this feature that allows you to schedule a single parachain to multiple execution cores is called elastic scaling.
And just another question, this might be like, we might be like getting out of time. So in case the block that was produced by the backing group, so backing group, since it contains 5 validators, there might be like disparity between them as well. So maybe like 3 might vote for something, 2 might vote for something. So is there a possibility that in case like there are like 3 votes for one thing, 2 votes for one thing, but eventually as a block they go with the majority, and in case like the block like turns out to be actually like it's a valid block, so when the rewards are distributed, only those validators from the backing group that actually supported it gets the reward and boost. I might be getting something
Yeah,
wrong.
so I already got lost in this example, and I will be happy to discuss it after this lecture.
Yeah,
Because if it takes multiple sentences to explain, like it's
Okay.
best to have like a one-on-one after the lecture.
Yeah, sure. Thank you.
Any other questions before we proceed? Here? Mike? Raise your hand.
I feel like this might be not dumb, but kind of like redundant, but I'm having a hard time keeping the order of everything, especially when it comes to like different situations that could arise. Is there like, not documentation, but is there like an animation? I'm very like visually based. So I'm just wondering if there's like that image of like axon, it feels like axons in cells. Like that's kind of what it reminds me of. But I wanted, if I saw that in motion as far as like information getting passed through these processes, that would make more sense to me, I believe. So I guess my question is, are there any, besides the docs, are there any references that I could see that kind of like more visually based? And if that's a weird question, I totally understand.
I think
the Polkadot wiki. There is
Yeah.
like
Okay.
there are a couple of pages.
Yeah.
Some are more introductory. The other one is specifically about elves.
Okay.
And yeah.
specifically those images.
Yeah, I need more of that. I just want more of, but like moving.
Yeah.
So, yeah.
wiki.polkadot.com.
Okay.
Yeah.
Okay. Yeah, sure.
I think that would be the best way to have any sort of like visual representation of how it works, but there is a lot of moving parts. Okay, anything else? Okay. So what you see on the screen now is a slightly simplified code example of how this like validation result might look after we run a PVF. And remember, the validator has access to the WASM blob, to the runtime of a specific parachain. All of those are explicitly stored in the state of the relay chain. This is all the cookbooks, all the runtimes of all the different parachains. And we also have the Merkle roots of all the state trees of all the different parachains. So we have their runtimes and we have their Merkle roots. And what needs to be actually provided by the collator is not just a list of transactions. Because remember, the validators of the relay chain, they do not hold the state of the parachain. So if we would just provide a list of transactions, for instance, Alice sends 100 tokens to Bob, well, the relay chain validator doesn't know if it's a legal operation because it doesn't know how many tokens Alice actually has, but it has the Merkle root. So the collator not only provides the transactions, they also provide a Merkle proof of all the state elements being touched by those transactions. This is what we call a POV, a proof of validity, is the list of transactions and all the necessary elements of the parachain state being edited by those transactions. And those two things, when you combine them with the runtime stored on the relay chain, allow you to see if this transition is legal. You have the previous state, the transactions, and the recipe to actually compute the post state. So in the end, the backer question.
So we are just providing a partial state.
Correct.
Okay.
We are providing the minimal amount of state needed to verify those transactions. So in an example of Alice sends tokens to Bob, we'll provide the balance of Alice to actually validate she has necessary funds to do the transfer. Okay.
I'm just wondering where the BOV is saved. I mean, for the relay chain, the BOV is the block for the pallet chain. So I'm expecting each validator has so many from other
Next lecture
yeah,
is all
and the
about
other
data.
validator, how they can validate that the data is it's correct. The validator is not cheating. So I'm expecting it could be saved somehow, or he is generating another proof, or what's happening under the hood.
Next lecture is all about that. It's called data availability, and it's specifically addressing this problem. And it is a real problem, and there is this very specific solution to handle that. Because yes, we do need to keep this information to make sure it's not lost, and it's not withheld from anyone. Any other questions before we proceed?
Hello. I have a question in the previous slides. This one, the code. So it mentioned we need a minimum state of parachain state to verify.
Yep.
But the signature of this function actually provide the relay chain's hash. Sorry, the other one, the next one. Sorry. Yes, the signature of the validate block. The second parameter is the relay chain hash. So I was wondering, how that this one is used, why we need this one.
So most of the data I mentioned is actually contained within the head data here. The relay parent and the relay chain hash is simply anchoring our computation to a specific point in time. A block has to be revalidated not too far away from its anchor. This is connected to asynchronous backing, which is something a tiny bit too complicated to explore right now. But the short story is asynchronous backing allows you to prospectively and optimistically back things into the future. But to limit how far into the future you can back, we essentially need to anchor stuff to specific relay chain blocks, specific relay chain ancestors. And this is the moment where it gets anchored and hooked. It's quite difficult to provide a much more satisfying answers at this point in time.
By the way, wiki.polkadot.com, there is a full page that has been peer-reviewed by, I think, 5-6 core developers about asynchronous backing. So I recommend, if you want to dive deeper and understand about parents,
I'm trying to search this method in the code base, but I don't see that. So I guess it's just a kind of
It's pseudocode that's a tiny bit different, and I simplified it a bit for the presentation. There's a few other extra things, but the logic is roughly similar. If you especially look for the signature of validate block, I'm sure you will find it. I don't think it was renamed to anything else.
Sure, thanks. I'll take a look.
And one more?
Yes, no?
Yeah, we can go.
Could you comment on the minimum number of validators needed on the relay chain side? And sorry, on the parachain side. Suppose it's a new parachain and not all 5 validators are up and running.
one of them goes down, only 4 are available. So now, how is that risk handled? And second question is, what if the...
No, before we go to the second question, let's focus on the first one. Slower and again.
Okay. On the parachain, instead of 5, let's say only 4 active validators are present.
Sure.
Now, is there a minimum requirement of 5 always? Or for new chains, the requirement are relaxed? It's okay to have 4 validators and then let them go through the whole protocol?
It's always 5. It doesn't matter if it's a new parachain or if it changes, it's always 5, and it's not something a parachain chooses. This is coming from the protocol when it comes to the backing group. You, as a parachain, you can choose how many collators you have, but you do not choose your backing group or who goes in your backing group and how big your backing group is. This is a fixed parameter of the protocol itself.
Got it. And second question, the validator on the relay chain side and the validator who gets bagged or whose block gets bagged on the parachain side, can both of them collude? I mean, can relay chain validator always
So we
favor...
call the parachain validators collators. We have a separate name to not confuse parachain validators and relay chain validators.
So can they favor?
So can they what?
Can the validators on the relay chain favor the same validator, same collator on the parachain? Is there a possibility of that? How is that
Favoring
prevented?
specific collators?
Yeah, like the same collator gets selected.
This potentially would be possible if your parachain is not using a throttling mechanism for block authoring. So if you are using Aura and there is a round robin, it's baked into the state transition function. The validator does not choose if someone makes a block. The state transition function defines through Aura who is the next block author. But if your parachain, and I don't think anyone does it, supports anyone creating a collation, then it would be up to the validator, if there are multiple collations, to select which one gets to be chosen. But this is generally not how it is done, because it would potentially lead to favoritism and because it's introducing a lot of unnecessary forks, which is wasted computation.
So how is it prevented? I mean, it's not ideal.
It is prevented by using Aura on parachain block authoring.
Got it.
And there will be a single parachain block per time slot, and that's it. The worst that can happen is the relay chain validator will simply refuse to accept your parachain block. But that's why we have 5 validators in the backing group. Even if we have a validator that dislikes you as a collator and they reject your parachain blocks, there can be a different validator in the backing group that will accept it.
Got it. Okay. Thanks.
Yep.
So, hi, Sid here. So my question was about the elastic scaling. If you have elastic scaling where you can allow more than one core for a parachain, why not make one group of one validator only? That way you have like more granular elastic scaling, and you can scale it up to 5 if there's need.
I mean, elastic scaling slightly out of scope, but generally speaking, the limit of 5 validators here has nothing to do with elastic scaling. We are having 5 validators here to have some potential redundancy if a validator wouldn't want to serve you for whatever reason, or maybe it's not even being malicious. Maybe this specific relay chain validator is simply overloaded. They don't have the capacity to serve you and get receive the parachain block from you. We want you to have alternatives where you can submit your parachain block.
Got it. Thank you.
Okay. one more thing before we go on the break. So when you run the PVF and you have the transactions, you have the partial memory state, and you try to evaluate it, you do it to know if the state transition is correct or incorrect. But what can even cause it to fail? So maybe the POV is actually malformed. Maybe you have this transaction from Alice to Bob, but someone didn't provide you Alice's state. Then you cannot even evaluate if it's correct or incorrect, the state transition. So you have to reject such a thing as incomplete. Maybe they decode correctly, but they don't actually lead to a valid state transition. You get some gibberish result, something that they didn't commit to initially. Or maybe the POV gives us a valid block, but it doesn't actually follow from the parent. So, you have the current state and you mutate it to arrive at the new state. But if Alice had 10 tokens, you add 100, and then you suddenly, technically the transition was correct, you're suddenly get 1 million. Well, it doesn't add up with what she had before. So once a backer actually verifies that a parablock is correct, they create and sign a backing statement. They essentially say, hey, I believe this parablock is correct. This is a receipt, a proof that they approve it. And all of this is to make sure that the backers put some skin in the game. Backers are validators, so they have a lot at stake, generally actually millions of DOT. And if they say a parachain block is valid, and if this is later proved to be invalid, they're risking 100% of their stake. This is the most malicious thing you can do, to say it was correct and fully vouch for it when it was not. The main goal of backing is not to grant us immediate security, because remember, we only had this one guy check it. From the perspective of the whole system, we don't trust this one guy. It doesn't actually give us security. But it gives us accountability. It gives us, if later on this is proven to be incorrect, we have someone on the hook. We have someone that will pay for it very dearly. So the backers are doing this checking not to verify true correctness for the system. They are doing it to protect themselves, because they are the one putting skin in the game. And the receipt, the statement, the signed statement that they believe this parachain block is correct is being gossiped around in the network, and it's being put on chain by the next block author. So then we actually know that this person can be held accountable. We have this data stored on chain in the actual state. But it's a tiny bit more complicated than that. We have 5 backers in a backing group. We are a bit more strict. We don't require a single backer vouching that this is correct. We actually require a quorum of 3 out of 5. So at least 3 out of those 5 have to say, okay, I believe this is correct, for it to be fully backed and to proceed. All of them have to actually risk something. This prevents situations where a single misbehaving, maybe not even malicious, but just there are some errors. A single misbehaving validator cannot accidentally back some malicious or incorrect state transitions. There needs to be at least a few others, so we know that there's something really fishy going on. It's pretty good because it protects honest validators from just accidentally backing something wrong. You always have some backup of your buddies also checking with you, and you gain more confidence, and we have more on the hook for potential punishments. And once we get this quorum of 3 out of 5, only then we fully broadcast the statements to all other validators in the active set. And once a block author, as I mentioned, actually spots enough backing statements, the 3 out of 5, he puts them on a chain as part of a block authoring inherent. So inherent is essentially a special transaction type that can only be submitted by a block author. It's always added when you author a block. And there is this special inherent where a block author always adds all the backing statements he has witnessed in the network. And we can actually investigate exactly what is in the specific candidate receipt being posted. We have a specific parachain it is referring to. We have the ID of the collator that is being responsible, is being held on the hook question, and the mic, if we have it somewhere.
There are 5 backers, right? So what, and we need 3 of them to say like this block is okay. So what if 2 of them are not answering at all? Do they get 100% slashed? If they do nothing, we don't have a receipt or anything, you know?
So 2 of them just do nothing or say that this is like incorrect or?
They say nothing.
Nothing happens, they're perfectly fine.
Happens, okay. So what is it, what if no one says nothing? Like 5 of them says nothing.
So if all of them do nothing, then this specific parachain simply doesn't progress. They're being stalled for a bit. And this is also why we do the rotations, because after a few time slots, a different group will be responsible for that parachain, so they will get some liveness and can progress. And I think this will be a good time to address the last final questions, and I think we have a break.
Yeah, it's just like a small question. You mentioned like each backing group should be only 5.
Correct.
What if the set of the validator is not dividable by 5? And we have kind of remaining or maybe less?
So there is generally all backing groups are 5. There is a very specific case where there can be a single backing group with less validators than 5. As long as there are at least 3 validators in it, they can still perform as usual. They can still get the 3 necessary backing statements. They just get less redundancy. Like if one of them is compromised or something, then this specific execution core, this backing group, will be dysfunctional and they cannot fully back anything.
Yes, this was when we have like a group less than 5. What if we have the remaining from the set is maybe 7? Like the number of validator set is more than, like when we divide by 5.
A backing group will never be more than 5.
It's kind of in the protocol itself.
It's just a hard-coded value. We simply split all the validators into groups of 5, period. Like it's not something a parachain chooses. This is like a relay chain specific protocol element that we divide them into groups of 5. Like we were exploring and actually testing in Kusama variants of that, having backing groups of size 3, 4. There are some trade-offs, some benefits, some downsides. I think there could be a whole lecture of exploring all the different trade-offs there.
Okay, so you mentioned they can be less than 5, right?
Yes.
So what if they are 3? So does that mean just only 2 validators have the right to say it is valid? Or how will it work if there are just 3 backers in the group?
So if there are less than 5, which really shouldn't happen in the real network, then if there are less than 3, then this backing group is fully dysfunctional. Like they cannot essentially back any of the candidates. If there's 3 of them, then if all of them agree, they can still back it. If there's 4, they have 1 potentially redundant. The only situation where a small backing group like that can happen is we have a number of validators that is not divisible by 5. But how many active validators is a well-defined parameter controlled by OpenGov, and they would have to be simply mistaken to set it to something not divisible by 5. It will be like a configuration error of the protocol. I think coffee break is in order. If there are any other questions, feel free to come over to me and we can discuss it. Yeah. So we have completed the first half of the data availability lecture, and now we are going to the actual data availability stuff, what it is, why we need it, what are the problems if we don't have it. So just to summarize, what we have done so far is we essentially collated all the transactions on the parachain side. The parachains have created this package for us that allows us to re-verify them, which includes their transaction and partial states. They send them over to the relay chain. They send them over to the specific backing group responsible for it. The backing group ideally re-executes it, and if they get a 3 out of 5 quorum, they provide the backing statements, and those backing statements get included in the next relay chain block, essentially hooking those specific backers as responsible for that parachain block. So what we have right now is we have a few relay chain validators on the hook for a specific collation. But as I mentioned, to re-execute this collation, to make sure it is correct, we need to have this POV, you need to have this data. If for some reason you would lose access to this data, then you don't know if it is correct, incorrect, or what exactly is happening there. And at this point, this data was only shared with that specific backing group. No one else has it. And they're the ones on the hook. So if only they have the data and they're responsible for it, what happens if they just don't distribute it? What happens if there is no data availability layer? So imagine a situation of a malicious collator. So parachains are blockchains. And each block in a blockchain has to reference the parent. If you cannot reference your parent, if you don't know what your parent is, you cannot make another state transition. So normally, a parachain block author, a collator, would, once they produce the collation, send it over not only to the relay chain, but he will also share it with other collators in their network so they can import that block and eventually in the future produce their own building on top of it. The actual problem occurs when they send the parachain block, the POV, to the relay chain, but they essentially prevent other collators from knowing what it is. So the attack scenario goes like this. They build the collation, but they selectively send it only to the relay chain validators, ignoring other collators. The relay chain will import that specific parachain block. Maybe it's completely valid. It's a nice state transition. Everything happens according to the plan. They can even accept it. It goes through. They back it. A lot of the other magic happens, which we'll be exploring later. But eventually, that parachain block gets finalized. Everything seems to be working fine. But other collators in this situation never received the actual data, never received the exact transactions and the state transition, because this malicious collator only sent it to the relay chain validators. So other collators now cannot build next consecutive collator blocks, next consecutive parachain blocks. They're essentially stuck because they don't have the parent, which was already finalized on the relay chain. So in this case, the malicious collator completely dominated parachain block production, In this case, only they know the most up-to-date parent, and only they can produce the next parachain block. So what's the solution? Validators keep enough information, the relay chain validators from a backing group keep enough information for collators to reconstruct recent parachain blocks. Validators cannot just discard collations after they do some of the verifications. They need to keep them for some time to guarantee data availability and liveness if it is needed. Then in the worst possible case, if there is a collator that withholds information, they can request it from the validators that approved and backed this data, and then those validators can send it back to other collators so they can continue building their chain. So POV needs to be recoverable from the validators. So can we just make backers keep it? Like, they're the ones that re-executed that parachain block. Why not them? Just make it responsible for it. But then that brings us to a malicious backer attack, another potential threat. And this essentially is an example of a centralized data availability. Because if only the backers have the data, it's a very small subset on which we depend on this data to be available. And the problem is we cannot really trust the backers to distribute it fairly. They can just ignore honest nodes when they need the data. And this can be quite heavily exploited by just not providing whenever it is requested. And for a parablock to proceed in its life cycle, at one point or another, others will need to verify it. And to do it, they need to have the necessary transactions, the POV, the partial memory state of a parachain. So the data is not only needed for the collators, it will also be needed in later lifecycle stages of the parachain block, so it can be further verified by other validators later on. So the attack in this specific case goes like this. If the malicious backer is the only entity controlling the POV, then other nodes cannot validate and potentially raise an alarm if this parachain block is invalid. And even worse, the attacker can distribute it to other malicious validators while actively withholding and avoiding honest nodes from getting access to this data. So it's creating this illusion of safety where some nodes get this data, re-execute and say, oh yeah, I think it's fine, while the other honest nodes, when requesting the data, just get ghosted and never receive the information necessary to revalidate it. So honest nodes know something is suspicious because they cannot retrieve the POVs to verify it, but it's impossible to prove. It's impossible to prove because how do you prove that the data was not sent to you? You can prove an equivocation. You can prove someone sent you incorrect data. There is no cryptographic proof to show they gave me nothing, they just ghosted me. And this is the problem we're having here. So if we create a data store that is not controlled by the attacker, then they cannot selectively distribute POVs. There has to be a different mechanism to actually store this data needed for re-evaluation. And eventually, everyone that needs to check something will be able to check it if they so desire. But the naive way would be to simply have every single validator store the POVs for every single parachain block. But well, we already went through the classic problem of data replication. The whole point of sharding is that everyone doesn't store everything. Like, this is what we're trying to solve. At least they would be holding only partial memory states needed for transaction verification. So it's not everything, but it's still a lot of data that needs to be held for a significant amount of time. We're talking about hours up to a day. It just does not scale. So To actually avoid it, we are using something called erasure coding. Did you guys discuss erasure coding at all at one of the first 2 days or PBAX? Who here is familiar with how it works? Okay, few people. So erasure coding essentially allows storing a limited amount of POV chunks. So not everyone has to store all of it. We're trying to encode this large data into smaller chunks and then distribute those chunks between the validators. And it all sounds pretty complicated, but it really isn't. I think a good way to visualize it is, imagine there's a line, and if you have 2 points on a specific line, this linear function, this line, is completely defined by those 2 points. If I give you 2 points, there's only a single specific line you can draw through that. And this is a first-degree polynomial. If you have 2 points, you can perfectly define it. And we can keep going further. If you have like quadratic, if you have 3 points, those 3 points only have a single quadratic going through them. You exactly would know what quadratic it is. And this keeps working further. If you have a third-degree polynomial, you just need 4 points to precisely define this exact polynomial. And now let's go back to the nice and simple line. What if they gave us 3 points on a line? Well, in this case, we actually have a bit more information than we need. We actually can lose or forget or remove any of those 2 points, but we can still recreate the same line. It doesn't matter which one we lose. It's still just the same line. And it's very useful when remembering the whole line is expensive, but remembering a few points is easier. Of course, there is the opposite situation. If, unfortunately, you lose more than 1 point in this case, then we are lacking information necessary to recreate this line. Now there are multiple potential lines going through a single point. So there is a certain threshold of how many data points we need to recreate it. In Polkadot, instead of a line, we have the data needed to verify. This is the POVs. This is the transactions. This is the partial memory state. And we simply encode all of this data, all of this POV, as a very high-degree polynomial. This is a very high-degree curve, a very, very, very curvy curve. And then we generate a bunch of points on this big polynomial. We generate much more points, many more points than we actually need to recreate it. So there is a lot of redundancy in those points. And each validator is effectively responsible for like a single point on this curve, for like a group of points. And a single validator doesn't have to store this big degree polynomial. They only store a set of points. But if enough validators get together and combine their points, we can essentially recreate this high degree polynomial and then decode it back into the actual data we need. And the good property here is that we don't need all the points. Remember, we created a high degree of redundancy in the points. There's many more of them than we actually need. So even if some validators maybe ignore our calls, ignore our requests, and do not send their points, their data chunks, we can still recreate the actual polynomial and the actual data. And the exact numbers are tuned that we only need 2/3 of the honest validators to provide us the points to recover the original data. So imagine validator Y is producing a block. Statements from validators of different kinds will essentially be determining the availability. So we are dividing the data into many, many different chunks. We're sending over the chunks to different validators. And then the whole point is trying to figure out when all the points are actually properly distributed between all the validators. So in this specific case, for instance, we don't see enough availability statements for some of the data pieces. For the first one, we see all the different validators, A, F, G, and B, saying, hey, I have received my chunk. And distributing those chunks is actually the responsibility of the backer group. After they sign their statements, they back their stuff, they gossip those messages, they also convert the POV into this high-degree polynomial. They create all those different points, and they send them around to different validators in the network. Each of them gets their own little piece of the data, which is much, much lighter than storing the whole data set. Question, if we have a mic somewhere? Where?
I'm just a bit confused with the process where the validators start to like sign or kind of broadcast the valid transaction to the block producer to be backed later on, and when he will broadcast the data to be in points to be like split it in the validator. I don't know how, but it's part in the mempool. How? Like I just like need if you can elaborate a bit on the steps.
Collator collates transactions. He builds a collation. Collation goes to the backing group. Backing groups, when it gets 3 out of 5 quorum, creates backing statements and receipts and sends it over, like gossips that in the network. The relay chain block author then sees the backing statements, and when he sees 3 out of 5 have backed, he includes the receipt on chain, and then we consider that specific parachain block backed. Then we proceed to the availability phase. Once it is backed, we are now tracking the availability of the data chunks. The data chunks are processed and created by the backing group. They essentially get the collation that they have just verified and they have signed, and they split it into those small little chunks, and they distribute it to different validators.
Here's my confusion, like as far as I understand, like the packing group, when they like send the statement that it's a valid block from the parachain, this is my assumption, like they also include the part related to the data availability where it will be splitted, or after it's get included, or the block producer say like, yeah, it will be included, they will after like send it back. This is where I'm confused. Again, you mentioned like the process where the parachain like submit the block to the packing group, and they verify once it's the 3 of 5 said okay, they start to have the statement, it's valid, and then they gossip it to the network, and if like the majority said okay, the block producer will include it. The part related to the data availability, like it should be issued, or like the data will be kind of broadcasted by the backing group itself. Is it correct?
The backing group itself will broadcast the availability statements once it is backed by enough people, and it is and the receipt is backed on chain by the block author.
It will be included in the receipt itself, or after
the availability.
Yeah, the availability statement.
It's a separate process.
Okay.
We first have the backing stage. The receipt is added on chain by the block author. Now it's backed. The backing process is at this point cut. It is done. Now we move to the second process of availability. The backing group now creates the availability chunks and spreads them around in the network. And we are tracking who has received their availability chunk. And we have something called availability bit fields, which is another thing that is in the relay chain inherent. So we have the backing statements, and we have availability bit fields. This is a separate thing that is going on the relay chain. And the availability bit field is essentially a binary map of which validator has received an availability chunk for a specific core.
And there is no way to misbehave the validator, like not to send this availability statement?
Oh, you very much can misbehave, and one of ways to misbehave in this case would be to simply not distributed availability chunks.
And they will be slashed?
This is very, 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 very difficult to prove, aka no. Because the hope is that this is also why we have 5 validators in the backing group. We need at least one of them to distribute the availability chunks.
Okay, thank you.
Yeah. Any other questions at this point in time?
We might maybe you might have slides for that, but just getting it there. So we decided not to duplicate all the things to each validator, but since we have sharded the data, does it now make sense to maybe make the shards available at least twice, if not not all the data is duplicated for everyone, but at least there are maybe 2 shards of 2 copies of each shards. Does that happen, or is it a single copy?
So the notion of a single copy or not doesn't make much sense here, because the whole data is encoded in such a way that we only need 2/3 of the validators in the network to cooperate to restore the data. So it's not a matter of a single copy or not a single copy. No one is storing the full data. Everyone is storing a very, very small part of the data. And if we have 2/3 of the validators cooperating, we can restore the complete data. So there is very minimal data replication here.
Is it possible for someone from the backing group to tamper with the data before they send it?
Yes, it is possible to tamper with it. That's why validators don't blindly accept the chunks. They will be verifying the chunks they received. So you don't send just the chunk. You also send essentially a Merkle proof of, okay, this chunks belong to you. This is the data I split into it, to verify that this is the case. But then after you verify the correctness of the chunk, you discard the data and just hold the chunk.
Okay.
Any other questions?
Any more?
Okay, let's keep going then. So this is actually answering one of your questions. What happens if there is a bad chunk in the POV? And Merkle proofs. We are making sure and we are re-verifying the actual availability chunks. And with each chunk, we are distributing a proof that it actually belongs to the Merkle proof and how it came to be. Okay, so the availability stuff gets a tiny bit more complicated, because what we can do is, ideally in most cases, the data is there on the availability side only as an emergency. We only recover it when we actually need it. We only recover it in cases where someone withheld the data from collators or other validators. In most cases, it is to recover the data at later stages, all you need to do is ping and request it from the backing group. And they still hold the data, but if they will refuse to give you access to the data, then you do a complete recovery from chunks. Complete recovery from chunks is a tiny bit consuming because we have to ping pretty much all the validators in the system and hope they send you their corresponding chunks. So this is a last resort type of situation. In fact, ideally, you first ping the backing group to get the full POV. Then if this doesn't work, what you do is some chunks are a bit more important than others and they hold more data. So we call them, I forgot the name actually, we call them systemic chunks. And then you try and ping the holder of systemic chunks. Systemic chunks are not as redundant. They, instead of holding a lot of extra data, they are the original data just split into smaller chunks. So for instance, instead of getting 2 further validators, you can recover the whole thing with just 10. If the backing group refuses to give you the data, if the systemic chunk holders refuse to give you the data, only then you ping everyone and do a full recovery from availability. So there's many different alternatives on the way where you can recover it, hopefully with minimal performance losses. And there's also a lot of improvements we can do to the actual erasure coding. Right now, we are using a Reed-Solomon implementation, and it is pretty expensive. Like, this is 15–20% of like validator CPU time, like doing all of this erasure coding of the data, distributing that. So if there are any optimizations to how we do it, this can improve our throughput by a lot. And there is actually a more performant implementation of Reed-Solomon that we still, I don't think, have implemented nowadays. And it's giving us potential very nice boosts. And it's still open ticket if anyone wants to maybe take over it. And I think one of my teammates did some benchmarks on this alternative Reed-Solomon implementation, and it literally gave like a 10x improvement. So it's not a meaningless bump. It's huge. So just to summarize, the data flows from the collators to the backers. The backers run some initial checks and back the collations. Collations are stored in erasure encoded chunks. This is the data availability layer spread over the network. And in general, we are getting 10 megabytes per execution core of data availability for 24 hours. This is how much potential POV can be actually mentioned in a single parachain block. Any questions about the data availability layer or backing process? Question?
Hi, Sidia. So when we, there's redundancy in the data that
Yes.
when we break it down, right? So how do I know that when I'm like recollecting them, 2/3, like 3 out of whatever, how do I know this data is not repeated twice, but is actually redundant part of the, like?
A very good question. So essentially, how do you make sure that there isn't a backing group validator just distributing the same chunk all over again to multiple people? The way it is handled is it is deterministic which chunk you should be getting when you create them. And there is a Merkle proof, a Merkle root for all the different chunks. And you can verify that you have exactly the chunk you're supposed to be getting with that algorithm. So, and it's also, the root is also included in the candidate receipt, which is essentially allowing you to verify that you have exactly the chunk that was supposed to be yours and not a different one.
Thank you.
And actually, the shards distributed are numbered, if I remember correctly. You
Correct.
exactly know like which part you're getting, and they are numbered, so you know you're getting the same numbers. Yeah.
So essentially, each chunk, you're not getting an arbitrary chunk. You're getting like your named portion of the data.
Hi, it's Paul here.
I would like to ask whether there were any alternatives for Reed-Solomon codes considered.
I don't know. I think it slightly predates my time, if it was ever even considered. But as far as I know, Reed-Solomon is pretty much the standard of how it is done. And I'm not familiar of any good alternatives that would offer similar guarantees.
Thank you.
Hi. So I'm actually confused about something.
Yep.
So how many backers are needed to like broadcast a proof across the network? And also, when do we know if it has been broadcasted so another backer is not going to like broadcast it again?
So technically, even a single validator in the backing group would be enough to distribute them. He needs to get the data, encode it, splice it into small chunks, and send it over gossip over the network, so it gets into their destinations. And then whenever, from the perspective of a different validator, when you receive your chunk, you re-verify it that this is actually your chunk, you check with the Merkle root and say, okay, this is mine, seems to be matching the actual collation. You then sign a statement, you gossip your statement that, hey, I have received this availability chunk for this collation. And this is getting gossiped in the network. And then the block author, in its inherent, is essentially aggregating all the availability statements from all the different validators and saying, okay, for this execution core, we have already like 55% of availability statements. And once we get to 2/3, then we are sure that this is actually available. We have more people have claimed they have received the chunk than we need to recover it.
Okay, so between the backing and the data availability, like what's the total time frame for it?
A single time slot, so 6 seconds. Everything is happening quickly.
Wow.
Hello. So you mentioned that there are some types of chunks. One of them was systematic. So how do we know on what basis they are chunking for systematic and other?
That's a good question. So essentially, like, how do we know who has the systematic chunks?
Like on what basis it will chunk systematic and other? Like systematic won't be duplicated.
So the first line of recovery is always to just ping the backers, because the backers have the full, decoded POVs. So you just ping them. There's 5 of them. Ideally, one of the 5 just sends it to you. This is the go-to case that solves 99% of situations. And systemic, I don't know exactly where do we get the info who has the systemic chunks. I would need to double check that.
Yeah, hi. Actually, I'd like a question as to like the Merkle tree for your, your chunks. So essentially, as part of the Merkle tree, you'd sort of get to know one of the other leaf nodes at the very end of the tree, right? So wouldn't you get to know about at least one extra chunk apart from yours? Or do we ensure that every chunk is divided into 2 leaves rather than 1?
Go again.
Essentially, like as part of the Merkle proof for your Merkle path for the verification of your chunk, you would essentially have to know one other leaf, right? As part of like the whole Merkle path. So in that case, do you divide each chunk into 2 leaves as part of the Merkle tree? Since if you don't do this, the other leaf would reveal one other chunk at least, right? While you're only supposed to know yours.
So there is no secrecy here. you can know other chunks. It's a matter of we don't want to store them long term. It's perfectly fine to know a different chunk and check how it is and check if it's different than yours. You just don't want to store it because you have to store those chunks. This is the promise. You store them for 24 hours. This is the data availability. We guarantee that this data is made available for 24 hours. So it's not a matter like in Sassafras where we have to like hide what you have and hide your tickets. Those can be fully public. It's fully in the open. It's just a matter of we want to minimize how much stuff we have to store.
Yeah, and when we talk about creating like different chunks of data, so is it that the complete block, that is those 5 validators, they agree on like creating those chunk, or only a single validator from that backing group creates that chunks and like divide that?
So the method is deterministic and all of them should create the same chunks anyway. There's a specific method of creation of those chunks.
Okay, so would they like each create their own chunks, but then that would like duplicate the chunks, right?
Good question. I don't know if one of them is like pre-selected to first do it or if they all do it at the same time. I would need to check the exact implementation details. I think it's quite probable that they simply, all of them like create the chunks and they start pinging like, hey, do you need the chunk? Hey, do you need the chunk? And they slowly start distributing them to different validators. Okay, let's focus for the last final stretch. This will not be a full-on lecture. I just have prepared some useful resources I want you guys to see that will be relevant to either the upcoming modules or maybe your future work in the Polkadot. We already covered some of the useful tools and the technologies. Here I will at least give you some links to maybe docs or where you can find them. So, another disclaimer. Polkadot is not just this core protocol. It's not just Parity building the Polkadot SDK repo. There is a lot of different external tools that either are maintained by different entities, different companies, different individuals, some of them public, some of them anonymous. One of a pretty good source that was revamped recently that I would recommend is just checking the polkadot.com website. I wasn't a huge fan of it in the past, but nowadays it's gotten a much, much better. It's linking to a lot of cool docs and giving you a lot of pretty nice like get started resources about what different wallets do we have, how is the token, how do you stake on Polkadot. Some of the primitives I was talking about are pretty well explained here, and it links directly to the Polkadot wiki. And overall, the Polkadot SDK is the main repo where most of the stuff, at least the implementation built by Parity, actually sits. And the Polkadot SDK contains 4 core elements. The first one is Substrate itself. This is the framework for building blockchains. And Substrate comes with its own opinionated version of how to build blockchain runtimes, the state transition functions, which is called Frame. In Frame, you will essentially be creating your runtime from small modular blocks. There will be a whole module later on in the PBA where you will be diving deep into Substrate and Frame and learning more about it. And Substrate, just to be clear, is not just for building parachains. Substrate is for building blockchains, period. But if you want to connect them to Polkadot as a parachain, you have a library called Cumulus. And it's essentially allowing you to convert your substrate solo chain into a parachain. It's adding all the necessary glue to connect to Polkadot to essentially inherit its security and messaging guarantees. And then we, of course, have the core Polkadot protocol stuff. This is all the backing magic I was talking about. This is the data availability layer. This is the core protocol logic. And then we have all the messaging elements of XCM, all the different instruction it provides and opens for parachains to communicate between each other. So if we would actually go to the Polkadot SDK repo, which I hope everyone here has seen at least at one point, and I highly recommend you to clone it locally, you will see some of the folders. You will see them in a second, I think. Once it's unstuck in a second, if you actually open the Polkadot SDK repo, you will actually see a separate Cumulus folder. You will see a separate substrate folder and get access to all of that information. Let's try again. Yeah, so if you actually go to the Polkadot SDK repo now, you can see a Cumulus folder, and this is where you can exactly inspect and see what is happening on the Cumulus library, how it glues together all the different elements. You can see the Polkadot folder. This is where you can inspect some of the stuff I was talking about the parachain inherent, where all these backing statements are located, where this parachain validity, validation, PVF, the parachain validation function is located. You can also see the substrate folder. And if we would actually go into the substrate folder, we'll have a bunch of stuff in there, but the one that is particularly interesting to you and will be probably quite interesting in the upcoming weeks is the frame folder. Because in the frame folder, we actually have a lot of different palettes. This is the small little modules that you can use to construct different runtimes. They're like plug and play pieces you can use to build your own runtimes. So for instance, we have the palette for balances. Most parachains actually run on Polkadot are implementing, they're having an instance of the balance palette. There's also some very dedicated palettes that are only used on the relay chain, but balances is used on both parachains and relay chain nowadays. But hopefully, as I mentioned before, balances very soon is going away from the relay chain to only exist on the parachains, to save as much computation on the relay chain as we can for securing parachains instead. We also have a palette for Babe, which is maintaining all the block authorship if someone is using Babe. And this is not the only repo that is worth investigating, because if you would prod in the Polkadot SDK one, you would notice that there is something missing. The actual runtime itself of the Polkadot relay chain is not there. It is held in a different repo called the Polkadot Fellowship repository. This is, how many of you have heard about the Fellowship or know what it is? Okay, I'm not going to be giving a full introduction to Fellowship, but essentially it's an on-chain structure formed of different experts from the Polkadot ecosystem that regularly contribute to the source code, regularly help maintain and secure it and share the knowledge about it. And they are generally the custodians of the runtime, and they're working on like the behalf of open governance. So whenever there is a runtime upgrade for the Polkadot itself, usually how it goes is they're cutting the runtime on the fellowship repo where they're making any necessary configuration changes, and then it's going up for a vote on the Polkadot OpenGov to actually enact the changes in there. And another thing worth mentioning, once the slides update in a second, is that Polkadot is the main network. This is the Polkadot relay chain and a bunch of partners around it. But this is not the only network in this whole ecosystem. Who has heard about Kusama? Okay, who has heard about Paseo? So Polkadot is the, the go-to network. This is the final production network with the highest security, with the highest amount of stake at hand. But Kusama is a little canary network. It's not a test network. I don't think there's a different parachain, a different ecosystem I know that actually has a canary network. So it's a different network, a copy of the original one, where the token is not valueless. It is there specifically to experiment with new features where the token is worth something. So it's not just a test network. So we can detect new problems, detect how features operate, and experiment on stuff before moving that into full production. So it's like a small scale production, and there are actual businesses running on Kusama and not on Polkadot. So it's more than just a test network. But we also have a place for a full-on test network, which is called Paseo. The token there is completely worthless. There is a faucet where you can get access to it if you want to just deploy and test something. And there's also all the different API libraries that you can use. For instance, Polkadot.js and Puppy Polkadot API, which I think you're partially aware of because of the lectures yesterday. And if we would actually go to Polkadot.js, if it lets me load it, Polkadot.js gives you a block explorer view. You can investigate individual blocks and see what is happening in them. And then if we would actually go into an individual relay chain block and see what transactions are in it, we would find this parachain inherent I was talking about. And if we would dive deeper into this inherent, we would actually find the backing statements, the availability statements I was talking about. We also have the government's sites. PolkAssembly, I think, is the most popular one. This is where you can see all the different referendums that are being currently voted on in the ecosystem. And just to be clear, just because you are a dev doesn't mean this does not affect you. There are a lot of runtime changes, a lot of upgrades being passed on there, which are affecting parachains, which are either enabling new features for them, or maybe doing recovery operations. If for some reason you stole your parachain, you essentially submit a new runtime that is devoid of any interactability, there is no call you can do there, you can stall your parachain, and OpenGov can help you unstuck it by resetting your runtime. So it's very useful to keep track on OpenGov and be aware of what you can achieve through it, especially in rescue operations. There's also a bunch of different wallets you can check, and then the Polkadot website comes quite useful. If we scroll down, we can see a few of the most popular ones. Nova, primarily a mobile wallet. Talisman sub-wallet, very useful if you want to make some transactions, you want to stake, and you want to you actually want to interact with all those different elements. And it will be invaluable to have at least one of those or Polkadot.js for the upcoming days and weeks. We also have all the staking dashboards. The Polkadot.com Get Started Staking gives you a pretty good introduction to all the elements in it. And if you would actually want to see the dashboards. There's the staking.polkadot.cloud to actually see all the elements, to connect your own wallet and nominate your validators and see your staking rewards and interact with the system. We also have all the Agile core time elements, which I haven't fully dived into yet, but we have platforms like RegionX or Deploy Polkadot, which is the PDP. They allow to either manipulate core time, so you can use elastic scaling and increase the throughput of your parachain, or just deploy your parachain for the first time with a single click deployment using PDP, which I think will be showcased this Sunday, exactly what it is and what it offers. And we have all the different smart contract hubs. We have, first of all, the Polkadot hub itself, Asset Hub, where you can use Solidity to launch some smart contracts. But you also can use other stuff like either Moonbeam, where it already has Solidity compatibility, or you can use Ink and write Rust smart contracts, also supported on the Polkadot hub. You have testing frameworks, which I particularly like is ZombieNet. It allows you to orchestrate and temporarily spawn a small Polkadot network on your local machine. You can specify, I want to have a relay chain with 5 validators, a backing group with the size of 2 parachains, and each parachain has 2 collators. A very few commands, you run it, and it immediately spins you up the small network locally. You can investigate all the logs. You can immediately connect to Polkadot.js or other block explorers locally and see how your local blockchain progresses and maybe test new features and how it performs in the whole ecosystem. We can also explore a bunch of current dApps. And if we scroll down, we see some of the most popular ones. If you'll be doing any sort of exchange with any sort of tokens, Hydration is the go-to decentralized exchange on the Polkadot space. Hyperbridge is an amazing bridging parachain connecting to a lot of other ecosystems outside of Polkadot. But it can even be used and leveraged to facilitate cross-parachain communication if you don't want to use XCM. We have some gaming ones like FIFA Rivals, and wallets, as I mentioned previously. Bridges already kind of covered. Dex is mentioned as well. Hydration, definitely check it out. And there's a lot of other very relevant community resources. For instance, the wiki.polkadot.com, highly recommended to have like a high level of different parts of the whole stack. It's not as coding related, it's just explaining the elements. For a more in-depth explainers, definitely check the docs themselves. And for very specific, I can't get this working, Stack Exchange is always there, and you'll get answers from people like Sean that lurk there a lot and answer a lot of questions. We have the Polkadot forum. This is where all the discussion of what's happening in the future of Polkadot, where should it evolve to, is actually happening. And quite a lot of people are watching Kusamaran, which is a YouTube coverage channel that's covering all the Polkadot news, if you want to get some intel of what is happening and what are the new things coming over. And this lecture is available to all of you with all the links. If there's anything of those you want to check out, please do, and I'm sure some of those links will become relevant in the coming days. But yeah, I think that's it from my side then.